Good afternoon, everybody. So it's my pleasure to introduce Aaron Zimmerman from the University of Texas, Austin. Aaron got his PhD in 2013 at Caltech, and then served as a postdoc and then as a research scientist at CETA, the Canadian Institute for Theoretical Physics, Astrophysics. All right. And since 2018, he's been on the faculty at the University of Texas, Austin. Besides being a faculty member there, he holds leadership positions within the LIGO collaboration and the LISA collaboration, as well as something called SXS, the Simulating Extreme Spacetime Collaboration for Numerical Relativity. Broadly, he's an expert on modeling and the data analysis of sources of gravitational radiation. So he works on things, besides the data analysis, he works, for instance, on semi-analytical methods, black hole perturbation theory, as well as interfacing with numerical GR. And so this will, I'm sure, all be part of what he will tell us about today. So
thank you very much. Thanks for the introduction, and thanks everyone for being here. I really appreciate the invitation. Let me say at the outset that I certainly can't cover all the topics I work on in this talk, or else we'd be here for a very long time, so I won't. And I also want to say at the outset that please ask questions. I'll have to try to repeat them back for the Zoom audience, so if I forget to do that, let me know. But I welcome questions. I don't mind if we don't get through all of my slides. This is for you, not for me. Today I'm going to be talking to you about gravitational waves and searching for the unexpected. It's kind of a two-part talk. So first I'm going to give you just an overview of the last 5 or so years of gravitational wave observations from my personal viewpoint. And then I'm going to tell you about some more recent projects that I've done with collaborators of how to use gravitational wave observations to search for the unexpected, basically new physics beyond the standard model. So with that, we begin with, or we don't. Hold on. The usual thing of you have to click before anything works in Zoom. Okay, first we begin with the first part of the talk, gravitational waves. So let me say, as Walter mentioned, I'm a member of the LIGO scientific collaboration, which is part of the larger LIGO, Virgo, KAGRA collaborations that collect and analyze gravitational wave data. It's a very large international community with many groups and more than 2,000 members. So I want to say at the out talk that this is not a talk on behalf of these collaborations. This is a talk on behalf of me. What that means is that as I tell you about these amazing results, all the credit gets distributed to all these people, and all the mistakes I might make or anything I might leave out, you can blame solely on me. All right. So I like to start these talks by just showcasing the real stars of the show, which are the experiments, the technological advances that have really opened up this new window onto the universe. These experiments are the twin advanced LIGO detectors, one in Hanford, Washington, one in Livingston, Louisiana, the sister detector Virgo near Pisa, Italy, and brand new to the network in just the last end of the last observing cycle and part of this current observing cycle is the KAGRA detector in Japan, which is currently able to observe at a lower sensitivity than the other detectors. At their heart, each of these experiments is a Michelson interferometer designed to measure the differential change between two arms set perpendicular to each other. But every single aspect of these Michelson interferometers has been souped up and carefully controlled in order to enable incredibly precise measurements, allowing differential measurement of delta L between the arms down to 10 to the minus 19 meters, less than 1/1000th the size of the atomic nucleus. That's, of course, sounds impossible, but it is routinely achieved, and it is what's necessary to observe gravitational waves, these ripples in the fabric of spacetime that come to us from the distant universe and provide only the most ghostly forces on these detector components. Even with this incredible sensitivity, gravitational waves have only been detected from the very strongest emitters of gravitational waves in the universe, which are binaries composed of very, very compact objects. So far, black holes and neutron stars, which orbit each other at relativistic velocities, emitting gravitational waves. What's depicted here is the gravitational wave amplitude, the dimension, the strain, delta L over L, as a function of time for a binary black hole merger, this is a theoretical prediction from numerical simulations, this signal is divided into 3 phases. The longest phase, the in-spiral phase, can last many millions of years in principle. And during this phase, the binary slowly sinks closer together, losing binding energy as it emits gravitational waves to infinity. And this phase is really interesting because it can be tackled with perturbative methods. Okay, so with methods from post-Newtonian theory, post-Minkowski theory, effective field theory methods, like those that Walter works on, this phase can be understood analytically to a great degree. But it is an expansion in small velocities, and eventually it breaks down as the velocities get very relativistic, and numerical simulations are what is needed to predict what happens as the black holes conduct their final orbits, merge together into a single black hole, after which there's another phase known as the ringdown, which can also be tackled perturbatively by perturbing around the final state in small perturbations. The result is this exponentially damped decaying signal that I'll hopefully have time to tell you more about near the end of this talk. One thing I want to say at the outset here is that in pure gravity, there is no preferred scale. And so the total mass of a given system sets the overall scale. This is time divided by some relevant time scale. So what this means is that for more massive systems, the time scale is longer. At a fixed distance before merger, the orbits are slower, and the merger itself happens at a frequency that's lower for more massive systems. This is important because for the lowest mass systems like neutron stars, those are lower in mass. They merge at a higher frequency. They'll merge out of our sensitive band. And this last portion of the process is not observable. All right. Even with these amazing detectors, and even with the strongest sources of gravitational waves possible, it is still a serious challenge to measure these waves, to detect them, and to learn something about them. And so I wanted to just spend a couple slides on the search challenge. This is the raw data from the Hanford detector. Buried in here is a gravitational wave signal, one of those chirping waveforms I just showed you. It's actually one of the strongest ones ever observed. So, I mean, I can see it, right? No. What you're seeing here at low frequencies is, of course, the detector noise oscillating away at characteristic frequencies of down to about 10, 20 hertz. We have a lot of noise at low frequencies. And then there's this faint fuzz on top, which is the high frequency noise. So what can one do? Well, the first thing you do is you go ahead and you whiten this data by applying a whitening filter. That puts the noise at every frequency on equal footing, and the result should just be regular old uncorrelated white noise. I still can't see the signal. Okay, so what can we do? Well, if you actually knew exactly what you were looking for and that it was in this stretch of data, you could bandpass filter it. And now finally, standing out above the noise is in fact the very first gravitational wave detection, 152914, which sort of inaugurated this era of gravitational wave astronomy. But you really had to know it was there to find it in the data. So how do we solve this problem of searching for a very quiet signal in very noisy data? Well, luckily, this is a well-understood problem since the early days of radar, and there is a nice solution known as matched filtering. The idea is, if you want to constrain yourself to filtering the data with a linear filter, there is an optimal filter to use, the thing you're looking for. You just go ahead and you take the waveform you're looking for, and you correlate it with the data, multiply it and integrate over it, and you get an output number, the signal-to-noise ratio here, and then you scan that across the data, and you'll get very small numbers until finally, if there's an actual gravitational wave hiding in there, even if it's not observable by eye, you'll get a strong correlation. This allows you to dig these signals out of the data. This is this signal-to-noise ratio detection statistic. It's actually a noise-weighted inner product of your template with the data, with the noise weighting given by the power spectral density. It just downweights the places where the detector noise is worse and upweights those places where you're more sensitive. Now, you might still worry this doesn't really solve the problem. Okay, well, what do you do now? You don't know every single signal. Well, we create these banks of filters. So basically, we map out the mass ranges where we want to actually detect things. We take our models coming from post-Newtonian theory, numerical relativity, and these synthesized effective models, which either come from physical motivations or are purely phenomenological, but which can predict the signal. And then we populate a template bank. Each of these points represents one trial waveform that we test against the data. And then all of these are scanned across the data in parallel, allowing us to maximize first over time and phase shifts, and then over the entire template bank in order to finally identify if in a given time there's a detection in the data. This works beautifully if the data is in fact just regular Gaussian colored noise. But unfortunately, this is not the full story. And detecting gravitational waves is not as easy as this is. In fact, the reality is that the detector noise is also populated with these transient instrumental noise events known as glitches, which unfortunately can look exactly like or very similar to gravitational wave events. Not exactly like, but very similar to many gravitational wave events. Here's an example of a type of glitch here, which is sweeping up in frequency and amplitude over time, very well mimicking a gravitational wave event. And so on top of the matched filtering method over template banks, the real secret sauce of all these gravitational wave searches is some form of signal consistency test, some goodness of fit applied to the output of these matched filters in order to actually tell apart a real signal from glitches. Okay. Now, what do we do once we've actually detected? Yes, there's a question.
In this plot, is there a reason for the regions that are empty?
Yes, that's a great question. So there's a distance in this space which is created by essentially this inner product metric, which is very non-trivial. And so it turns out that, for example, down here, there's an enormous density of templates because two things that are very close in mass are very far apart in terms of their correlation distance. So first of all, the templates are going to be naturally sparser out here where that distance scale is actually larger. The other thing is that these things are constructed in a very complicated way because populating a template bank efficiently is one of these very difficult sort of tiling a high-dimensional space problems. And so it's very hard to solve that in a good way. What was done here is that already there had been detections of gravitational waves in this range. So the template bank was seeded in this region densely, and that allows these empty regions to be sitting next to it. Great question. Any others? Yeah.
Is that assuming anything about the inclination of the source of orbit?
That is a beautiful question. So the inclination to the line of sight tells us about the actual mixture of the two independent polarizations we receive. The reality is that currently there are no full-scale searches. Just this year there's a new one, but before that there's no full-scale searches that scan over that particular parameter. Instead, we have to do a more limited parameter space in practice, which causes the searches to be a little less sensitive than they could be in principle. So instead, this just in some sense marginalizes over that uncertainty by ignoring it and just using the imprint of the waves on two different detectors. So we're insensitive at this level to the inclination. It's a great question. Others? All right. However, here's where we learn about the inclination and everything else we want to know. Okay, what do we do once we actually detect a signal? Well, once we have a target stretch of data to study, we can go in much more depth and use a much higher dimensional model than those simple template banks that I mentioned before. What we do in our field is what's called Bayesian inference or Bayesian parameter estimation. We try to solve the inverse problem. Given the data, we want to figure out the probability distribution that certain parameters of the binary were the ones that made the data. And so our goal is to get these posteriors, right? These are the probability distributions that the system has a given set of parameters theta given the data we measure. And in order to actually calculate these probabilities, we have to turn the problem around with Bayes' theorem and convert it into a few terms that we actually can compute, because it turns out this we just cannot compute. But these other terms we can. So the first thing we have is the likelihood. This is the probability that you got the given data, assuming a priori that there happened to be a signal with a certain shape in there. So this is knowable because the difference between the signal you're assuming and the data you got is just the noise. And that's a random number you can understand. The devil of all of Bayesian analysis is this idea of these priors. You also need to specifically phrase what your prior assumptions are on all the parameters. You can use these to your benefit. For example, you can demand all the masses be positive, okay? Or you can incorrectly use them to put your thumb on the scale and, for example, bias your measurement strongly by phrasing really strong priors. So this is sort of the source of every single argument everyone has about Bayesian statistics is what are your priors? But at least you actually have to state them explicitly before you move forward. Finally, this evidence parameter at the bottom is just a normalization factor for the purpose of this talk that makes sure that the probabilities sum to 1. And so what I'm going to be showing you coming up are these sorts of measurements. Okay, when we measure the parameters of a gravitational wave signal, we display these probability distributions in, say, mass space, showing you where the masses are more probable and where they're less probable. And we also show these marginalized distributions integrating down, projecting down to one-dimensional probability distributions. So this is our way of measuring things. All right. With that, I'll just go ahead and skip this for now in the interest of time. With that, let's go ahead and talk about the data. Okay, so the observing runs today. So the way this works is that the detectors will run for an observational campaign, detecting hopefully a bunch of gravitational wave signals, and then they'll shut down for upgrades, improvements, and commissioning. And so there have been a sequence so far of 3 complete runs, and we're currently in the middle of our 4th observational campaign, with each of these gaps being an opportunity to improve the detectors. The result is that even though each of these observational campaigns have been sort of similar in length, the amount of detections has gone up rapidly because of the improvements made to the detector. One of the really cool things about gravitational wave detections is that we measure a field coherently. We measure a field coherently rather than an intensity. What that means is the thing we measure falls off as 1 over distance, not 1 over distance squared. What that means is that if we double our sensitivity, we double the reach, which we can see things in the universe, which means a factor of 8 in terms of rates, because we pick up 8 times the volume by doubling our sensitivity. That's why we go rapidly from first campaign was about 3 detections, next one was 8 more, and then 81 more, right? So it's these small improvements in sensitivity are leveraged to huge gains in terms of our data set. This is just a summary plot for artistic purposes of all the detections through the 3rd observing campaign. What is being depicted here is each binary that we measured as a pair merging into its final product, plotted as a function of mass, so in solar masses. You can see the vast majority of our events were binary black holes, most of them with masses between 20 and 30 solar masses for the components, with a few of these outliers. Each of these represents sort of the end of the life of some binary set of stars, which lived out its life as a binary, collapsed, the stars died, and then they were able to eventually merge under gravitational waves to form a final black hole. Now, I could spend multiple talks telling you about all of the interesting events in this data set. Some of them I'm actually friends with, other ones I couldn't remember a thing about. But for the purpose of keeping this talk short, I'm just going to highlight some of the new and exciting things that happened in our 3rd observational campaign. To date, we've detected 90 events. I'll focus down on just a few of them. So the first highlight from our 3rd observational campaign was actually a second. It was the second detection of a binary system of neutron stars. Okay, all of our events are labeled by their address and time. 1904-25 was April 25th, 2019. And the thing that was really interesting about this particular event was actually that it demonstrated a newer capability of our data analysis pipelines, which is that this was essentially a single detector detection. Okay, it was really only observed strongly in one of the 2 LIGO detectors. There was the 3rd detector, Virgo, was on at the time, but didn't really provide detection information itself. And this is actually surprising because if you've heard much about gravitational waves, you've probably heard that what we do is we look for a signal in one detector and a signal coincident in another detector at sort of the same time delay. This is a very natural way to do a signal consistency test, right? If it's one of these glitches, it's only going to happen in one detector at a time, not in both at a very specific time delay. But in fact, the signal consistency tests are sophisticated enough now that we can make confident statements. So what's being plotted here is the matched filter output on the horizontal axis, a signal consistency test on the vertical axis, and this is the background noise. This is this particular detection, standing far out beyond the noise, even though it was only detected in one detector, and allowing us to make a confident detection statement about this event. This is great because we don't always have both detectors on at the same time. On the other hand, unfortunately, when we only detect in one detector or 2 detectors at a time, we're very bad at localizing the event in the sky. What's being depicted here is the probability distribution in the sky of where this event could have been. And it could have been basically anywhere in the whole sky. Okay? That makes it very hard for astronomers to follow up on this event. And even though it was a binary neutron star, which could be accompanied by a gamma ray burst or an emission of light called a kilonova, no good candidates were detected from this event. What was interesting, though, is we can still learn about this system just from the gravitational waves. We can get very precise measurements of the mass, of the spins, and other properties of the objects we observe. What was interesting about this particular system is that as a binary of neutron stars, its total mass was sitting out here above 3 solar masses, which was a big outlier compared to the distribution of binary neutron star systems we've seen in our own galaxy. So this shows that with gravitational waves, we're beginning to explore populations of binaries of compact objects, which are totally different than things we've seen before. And this may be because of selection effects and radio surveys or any number of other issues that prevent us from detecting these sorts of heavy mass binary neutron star systems. All right, that was one of the first highlights from the third observing run. Another really interesting one was one of the heaviest systems we've ever detected, 190521, which was sort of talked about as the first intermediate mass black hole, meaning that these two together merged and formed a final black hole above 100 solar masses, the first time such a heavyweight black hole has ever been detected. Individually, the mass of this system, you can see, were about 70 and 60 apiece. And this is really interesting because actually, it is a real puzzle how you form black holes of this particular mass. Okay. Black holes are formed at the death of some massive star, right? Its core collapses, there's some tremendous supernova, or maybe the whole thing collapses and we don't see a supernova at all. The heavier the star, generally speaking, the heavier the remnant black hole. But it turns out that above about 40 solar masses for the black holes, the progenitor star would have to be so massive and so hot in its interior that it would pair produce electron-positron pairs. As soon as you pair produce electron-positron pairs, you rob all of the radiation pressure from the core. The star collapses and explodes in a really violent event called a pair instability supernova. This puts a natural cap on the expected mass of black hole systems. And this was above that, the predictions of that cap at the time. Now, stellar evolution people have sort of modified their models a little bit. It is possible to create these systems this massive, but this was sort of a stretch at the time and maybe gives an indication that this is a second generation merger, meaning that one of these could have been formed by a previous merger of binary black holes. Another really oddball, one I found even more interesting personally, was this other one, 1908-14. This system had exceptionally well measured masses. Okay, look at the accuracy here. These 10% accuracies are extraordinary for an astronomical mass measurement. The primary was about 20 solar masses. The secondary was north of about 2.5 solar masses. And this is very interesting because the secondary then poses a puzzle for us. This is heavier than most any model would allow for a neutron star to be. Okay? Neutron stars of these masses would tend to collapse to form black holes by the time they got this heavy. On the flip side, it is very bizarre to have a black hole in this very low mass. This would be the first of its kind. And we can't tell from the gravitational waves which is the case, whether the secondary is a super light black hole or a heavyweight neutron star. But time will tell. And even forming a system with such an extreme ratio of masses is quite challenging from an astronomer's perspective. So as we continue to observe, we hope to see more of these oddball systems so we can understand better where they're coming from. Yes.
Can you back up? I want to ask two questions. One,
Yeah, of course. Oh, sorry about that. I don't know what just happened. Yes.
You were talking about finding heavier pairs than had been found in other surveys, but you're biased toward heavier.
Yes, that's a great question. So absolutely. So this is a single measurement. So this is not accounting for any selection bias. And you're absolutely true. We are extremely biased. Our gravitational wave observations are heavily biased towards more massive systems. We see them further away. So this is not at all a population statement. Okay, but with a few more such measurements of these systems, what we can eventually do is we can start to figure out what is the distribution of masses of the neutron stars we're seeing. So we do have the selection effect, and for a single measurement, that can't be accounted for. That's right.
Okay, and then the second question is the next slide, the issue of genders being too massive.
Yes.
It's also just accreted mass, right?
This would be a rather large amount of accretion. So if these were supposed to top out from pair instability at, say, 40 solar mass, they still would need to accrete 10 to 20 solar masses of material, which is very, very extreme. So more likely a standard sort of astronomical channel for these would be that, in fact, they have enough mass loss during their lifetimes that you can get a core of the right mass without them going through the pair instability. This is not my area of expertise at all, but that's, I think, the main uncertainty in these mass caps were from models of wind losses during the life of the star. Other questions? Yes.
You said that time will tell about the exact like event that produced this.
Yeah. Great. Time will never tell us more about this event. These are transient explosions. They happen once they're gone. But we're surveying the universe. And so anything we see is going to be part of a larger population, maybe an outlier, right? In which case we have to make many observations before we'll see another such outlier. But generally speaking, this should be, right, the member of some population. And so over time, we'll hopefully see more members of this population, some of them with stronger signals. The stronger the signal, the more we can learn about those systems. So we may never be able to measure whether or not this was a neutron star, or even whether others of this category are neutron stars. But maybe one day, we'll get enough of them that we'll understand better the population hierarchy, and we'll convince ourselves, no, there really are neutron stars of these large masses. Maybe because we see them paired with other things where we can get electromagnetic information. Thank you. Other questions? All right. The last thing I want to mention about individual events is the last sort of exciting new thing from the third observing run was sort of our last sort of stamp in our collection. Okay, we'd seen binary black holes from the beginning. Binary neutron stars were first seen in the second observing run. One question was whether we'd see pairings, neutron stars with black holes. And indeed, we saw two such systems 10 days apart in early 2000, GW 2001-05, GW 2001-15. These are two neutron star systems. You can see them in blue and red for their mass system estimates. These are sort of firmly in the range of what's expected. Both of the secondaries have masses as expected for neutron stars. Both of the primaries have masses favoring black hole origin. The first of these two was, again, a single detector detection and less firm and also poorly localized. The second was a two detector detection and is a very secure detection, but it was still only observed with, I believe, two detectors, and so its localization is not very good. And again, in none of these cases was there an electromagnetic counterpart detected coming from these events. Nevertheless, this allows us to sort of take a step back and look at a whole sort of new range of systems that came out of the third observing run that we hadn't been seeing before, which are systems of more extreme mass ratios. I've got the two neutron star black holes. I've got that 1908-14 weirdo I already mentioned. And then there's some less significant detections, less secure, but still we have these mass measurements for them, which begin to map out a whole series of systems at very high mass ratios, which could be neutron star black holes. As we collect more and more of these, we can again begin to do population studies and come to a better understanding of these systems, which have not been observed in any other way than by gravitational waves. All right. This is what we do when we talk about single systems. An individual system can teach us something new if it sort of breaks all of our assumptions. But we now have 90 compact binary detections. And so the natural thing is to do population studies with them. And here we have to account for our selection function. And we do account for our selection function. And the result is that, for example, we can plot the mass spectrum of the binary black holes in the universe. Okay, so we only detect systems at the higher masses. But by accounting for our selection effects, what we can say is that, in fact, there are far more at lower masses than there are at higher masses merging in the universe. With 90 events, we can begin to tease out some features of this. This is still sort of a model-dependent plot. It depends on what models you use. But whatever models you use to sort of fit the mass spectrum, a few things are showing up very clearly. For one thing, this is primarily a simple power law. But there is some sort of bump here, an excess of binary black hole systems at around 30 solar masses. It is not known where this is coming from. Okay, so this is already a mystery for stellar modelers and astronomers to solve. Another thing that's very secure here is that even though we did detect that one heavy mass system, this falls off very rapidly at high enough masses, leading to a dearth of black hole events at very high masses, indicating that something about that parent stability story really might be at play. Okay, we would be detecting these systems if they were out there because they're so heavy. We also get a total rate of these systems, around 20 per cubic gigaparsec per year. But what's interesting actually is with the third observing campaign for the first time, we can map out the rate history of the universe for the first time. So we can see that the measurements tend to favor an increasing rate of binary black hole mergers with cosmic time. In fact, tracking really well the star formation history so far. Okay, this is totally as expected, and as time goes on, we'll increase our reach and get a better understanding of how these rates changed over cosmic history. Another thing we can do is we can actually measure the spins of these systems. Okay, one of our measurements actually allows us to see if these systems were spinning. The components of the spin aligned with the orbital angular momentum tend to speed up or slow down the process of binary inspiral. And if there was components of the spins not aligned, then the system as a whole precesses over longer timescales, causing modulations in that simple chirp waveform I showed you, which we can measure, and therefore measure the spins, both the spin magnitudes and their tilt with respect to the orbital plane. And so what we can then do is take all of those individual measurements, none of which are especially good, and talk about the population of spins. Here, this is the population, the probability of the dimensionless spin, the dimensionless angular momentum, which goes between 0 and 1. 1 would be a maximally spinning black hole just on the cusp of becoming a naked singularity. And what we find is that we do see that the population tends to favor spinning. Okay, on the whole, these black holes are spinning, but they're not spinning close to extremality. Even more interesting is to look at those tilts of the spins with respect to the orbital plane. The reason is that this can tell us where these black holes are being born. If they're born by two stars that were born together, spent their whole lives together, the spins tend to be correlated with the orbital angular momentum. And so we would expect these tilts to tend to be small. We would get a big peak of probability at spin angles close to 0. Okay? If, on the other hand, these systems are being assembled dynamically in really dense stellar environments, so the two black holes weren't born together, but instead found each other later in their lives, the spins would be totally random, and we would expect a uniform distribution. We see neither. Okay? Instead, we do see evidence that some of these are coming from a dynamical origin, because we see some systems that are misaligned with their orbital angular momentum. But this is not just a flat distribution. It does have some preference for alignment, demonstrating that there's probably two channels. As time goes on, we're going to continue to measure more and more of these systems, to sharpen up these measurements, and to start to actually tease apart these different origin stories. Now, those are the kinds of astronomy, I would say, things we can do. Sort of map out the population of black holes, figure out where binary black holes are being born in our universe. But we can also do a host of fundamental physics things. Okay? We can, for example, by detecting neutron stars, we can actually measure how much they deform each other and learn about the interior structure of neutron stars. So we can do nuclear physics with our observations. Of course, this is gravitational wave astronomy. We're observing black holes smashing together. So a natural thing to do is to do tests of relativity. We can test the propagation of gravitational waves through the universe. Do they disperse or not? We're sensitive to that. We can also do parameterized null tests. We can tweak our models with some free parameters and see if they're constrained to be 0 using the whole population. Finally, we can start to do cosmology. One of the neat things about these events is that they are standard sirens. They have an absolute luminosity which can be measured from the signal. That means we can measure the distance to them by measuring the actual luminosity we see them at. Okay? Unfortunately, they don't provide us with a redshift measurement. So you can't naively do cosmology with them unless you can localize them to a galaxy somehow. And so if we get an electromagnetic counterpart, we can do cosmology. Otherwise, we have to do statistical studies by sort of cross-correlating our observations with galaxy catalogs or population information. The result, though, is that we can, in fact, measure the expansion rate of the universe today. It's not a great measurement of the Hubble constant when you put it next to CMB or supernova measurements, but it's actually not that bad, and it's getting better and better. So the hope is that in the future, from pure gravitational waves, we'll be able to provide with our own unique systematics, not systematics free, but our own unique systematics, a measurement of the Hubble constant to within a few percent, perhaps playing the role of deciding between these two different measurements of the Hubble constant that people are talking about as a Hubble tension today. All right. That is the end of the first part of my talk. From here, I'm going to go into some more of my own research, but I think it's a good opportunity to pause and see if there are any other questions related to the first part of the talk. And now I'll try to remember to repeat those questions. Yes?
Way back when you said you have a map of theoretical models.
Yes.
How confident are we about like lack of degeneracy, or like this really is all the stuff that is reasonably could happen, or what? In other words, we're not fitting to the right things.
That is a great question. So the question was, how confident are we in these waveform models? Are we losing any physics? Are there severe degeneracies? This is an open subject of investigation. So this is a whole community of people working on these models. So as I said, we have different techniques for modeling the different pieces of the process. And then on top of that, okay, we have to tie these together to create practical models for data analysis, because we can't do a numerical relativity simulation, which takes weeks or months, per evaluation of a likelihood function. That's impossible. Okay, so there's two different kinds of uncertainties. One might be fundamental theoretical uncertainties. And luckily there, for binary black holes, we're good. Black holes are the simplest objects in the universe. They're determined fully by their mass and spin if general relativity is correct. And so we know exactly what the parameter space is here, and we can simulate it on computers or input it into our models. The real question is, are we using all of that dimensionality in our models? So for example, almost every model we use assumes circular orbits. The reason for that is that you tend to emit your eccentricity faster than you emit your semi-major axis. So most of the systems should be very circular by the time they enter our band. But in fact, that could be a source of error and systematic error. And so there's a huge community of people studying the effect of eccentricity. And we do not yet have good models which incorporate both orbital precession and eccentricity. That's the frontier. Okay? But as time goes on, the waveform modelers have been incorporating more and more of those physics things that we know in principle, but not in practice have implemented into these models. So we're in pretty good stead today, except for those questions of eccentricity. Other questions?
I could ask one.
Yeah.
So do you know that the rate of events is so low that you can also only use just one model per bin?
Yeah, that's an excellent question. So we do have the rate measurements now. These are rare. I mean, you know, in aggregate, we've run for more than a year, and we've seen 90 events, and they last from a minute to fractions of a second each. So we're pretty good in terms of these rates at the current sensitivity. So overlap is not something we're worried about yet, okay? But if I get to the very end of the talk, we're, of course, planning very ambitious future projects where we will observe systems all the way out to perhaps before the first stars ever formed. And in that case, actually, we will see many events all piled up on top of each other. In particular, binary neutron star waveforms, in that case, can go on for minutes to hours, and they'll have things laid on top of them. So that is a problem people are actively investigating in preparation for experiments we hope to build in the future. Sorry, the question was whether there was pileup of the events or whether we can just really rely on having only one event in the data stream at a time. All right. If there aren't any other questions, then I'll at least get to talk partly about the second half of the talk, which is searching for the unexpected. So a natural question I might have expected someone to ask before now is, wait a minute, you just said that you're using match filters. So you have to know what you're looking for, or you can't find it. That seems like a bad strategy for someone that wants to survey the universe, right? Can you detect things that you weren't expecting to detect? Okay, and it's a great question. We need a model to use match filtering. And so what can we do to detect things we didn't expect? Well, luckily, people have, of course, spent time developing searches for unmodeled gravitational waves. You do then have to rely on coherence. You look for a coherent power in multiple detectors at the same time. That allows you to detect things you didn't expect. But the interesting thing is that those searches, those coherent burst searches, they are best at detecting strong signals that are short. And they are challenged by detecting longer signals that are at lower amplitudes. Okay? So there is, in fact, a discovery space, as was pointed out by some of my collaborators in this paper in 2020. There's a nice discovery space here for low mass, long duration signals that are different than we expected. So how can we search for such things? Well, let me just double down on the why, on what we can do here. Let's imagine we had a low mass binary system, but something about that binary was a little bit different than our expectations. Okay? We can miss that because a very small change to the system parameters can cause it to dephase with our expectations in the match filter over time. And for a long enough signal, even a very small difference in the waveform can eventually lead to a non-detection. What this means is that we want to focus here on capturing this dephasing, but if we focus on very long signals, one of the benefits is that if these are very long signals coming from low mass systems, remember I mentioned that the merger would be pushed all the way out of bounds so that we don't observe it. So what can we look for? Let's imagine that there were boson stars out there in the universe, or some other object fluffier than a neutron star, but still compact enough to produce gravitational waves strongly, okay? That would have a set of source properties which would cause this dephasing. And of course, we wouldn't know what happens when these objects merge, okay? That might be something completely unmodelable. But if all we observe is the in-spiral, we can, in fact, model that. And I'll talk about how we do that now. Kappa is the spin quadrupole moment. I'll mention that. Okay, so let me talk about that. So what if we had these objects, these hypothetical compact objects, something exotic and new, which we don't know much about them? How do we possibly model them? Well, during the in-spiral phase, we actually know exactly what to do from effective field theory type perspectives, okay? When the objects are far apart, we can treat them as point particles dressed with some additional information. Okay, for example, they might have spins, and those spins interact, and we know exactly how that affects the in-spiral. Or they might have intrinsic multipole moments. They might just have, sorry about that. They might just have a physical quadrupole like Jupiter and Earth do, right, which impact their gravitational wave emission. Now, for extremely compact objects, it seems extremely unlikely that they would have any intrinsic multipole moments beyond their spin. Well, what they do have is polarizability, okay? In other words, if we have an object and we set it spinning, it will deform from being a sphere to an oblate spheroid. And that gives it an additional quadrupole moment. The amount of quadrupole moment it picks up is encoded in a dimensionless parameter kappa, which is 1 for black holes. We know that theoretically. For neutron stars, it's around 10. But for big fluffy objects like hypothetical boson stars, this could be in the hundreds, right? This, in turn, changes the binding energy of the system and enhances the gravitational wave emission, meaning that having such a spin quadrupole moment will speed up the in-spiral, and that's a detectable effect and would cause dephasing against our actual standard templates. Or, famously, the tidal fields of the companion will cause a deformation in the object, which is the size of that deformation is encoded in a dimensionless Love number, which we think are the order hundreds for neutron stars. But again, for some hypothetical object, could be hundreds of millions, potentially, okay? Again, this kind of extra quadrupole moment imprints itself on the gravitational waves, and this is precisely how we've actually measured the tidal deformation of neutron stars with gravitational waves, which in turn, by measuring these lambda parameters, allows us to understand the nuclear physics of these neutron stars. The nice thing is that once we take this perspective of dressed point particles, we already know how to do all the modeling. It's just standard post-Newtonian perturbative theory, and we can write down the waveform models. All we need to do is promote these polarizabilities to free parameters. We don't assume what they are for black holes and neutron stars. They're just free parameters. They're an extra dimension to our template bank. That poses us a challenge. We have to search over a larger template space, and that's computationally very difficult. So with a group of collaborators, we started to investigate this project in order to understand how can we develop new targeted searches, direct searches for hypothetical objects while still keeping these searches computationally feasible. And as a sort of proof of principle, we targeted this idea of tidal deformation. Our model is going to be that we're looking for objects that have negligible spin, but potentially are, again, fluffier than neutron stars so they can be largely tidally deformed. This plot depicts, as a function of total mass of the system and the log of a tidal deformability parameter that encodes the deformation of both objects, where current searches would fail. Okay, if the tidal deformations are above about 10 to the 3, you would begin to not find them with current searches. And so all of this between 3 and 7 in order of magnitude is basically open search space that we can look for. So by focusing on just tidal deformations, we have a 3-dimensional model, which compares well to the current search space of 4 dimensions. And so we can actually run such a search. Now, what kind of objects could we be looking for? Again, this is all very hypothetical, right? This is sort of a pie-in-the-sky search, hoping that you detect something really exciting and new. But if you don't do it, you won't find it. Some of the actual things people have studied theoretically would be, for example, boson stars. You have a massive scalar field. Massive scalar fields can actually condense and make compact objects of astrophysical scales. And so for certain coupling parameters and certain masses of the boson field, we would actually produce boson stars with masses in the range that we would be able to detect them in binaries. Or, and I think this is one of the most exciting speculative ideas, what if in the universe there was a very light particle, sort of an axion-like particle with masses deep down in the like 10 to the minus 12 eV range, okay? People have started to think about particles like this as potential dark matter candidates. Well, if the mass is such that the Compton wavelength of this hypothetical particle, right, is about the same size as a black hole, it turns out that black holes will spontaneously dress themselves in a cloud of these particles. The black hole will lose its spin energy, and it'll dump that into a massive cloud of bosonic matter around it. These are sometimes called gravitational atoms, because you can basically study them with a Schrodinger equation, okay, and understand their energy levels and the properties of these clouds. This really would happen if these light particles existed, and observations of binary black holes amount to searches for these sorts of light particles. But this would effectively give us a sort of fluffy object with an extended mass that we could detect with our search. Similarly, one can look at scalar fields with quartic interactions. Those also produce stellar mass boson stars. This is just a slate of the kinds of things we could maybe detect with this search. So we carried out this search, not using the standard search codes used by the LIGO, Virgo, and KAGRA collaborations, but by actually a code developed externally at the Institute for Advanced Study in Princeton by some people I know. This is a very sophisticated search code. It's able to detect all the same binaries that the LIGO, Virgo, KAGRA collaboration has detected, and even by their own claims goes a little bit deeper, okay? We used it because we could modify it easily, and we targeted a range of massive systems between 3 and 15 solar masses, and these are the results from 01, 02, and 03. What we have here is a cumulative number of candidates at our certain detection statistic, which is what's called the inverse false alarm rate. This is how long you would have to wait till pure noise created a signal of that particular sort of goodness of search statistic in your search, okay? So these are our actual measurements, and they're perfectly in line with the background model, which is the red. So we didn't detect anything, okay? We ran the search, we actually looked for these systems, and we detected nothing. So what can we do with that? Well, what we can do at the very least is put a rate bound on the rate at which these sorts of mergers happen in the universe, and we constrain it to be a similar level to the rate at which we've detected binary black holes in the universe, which is to say a few times 10 gigaparsecs per cubic gigaparsecs per year across our search space. Okay, so bit of a disappointment, but it does at least allow us to constrain the rate at which these events are happening. And it is, again, just a proof of principle that we could search for such systems. Now, one of the big outstanding challenges here is how we can use these kinds of rate constraints to constrain beyond standard model physics, right? And this is, I think, a big open challenge, okay? It's one thing to say that, oh, if there were a boson star, we would, in a binary, we could have detected it. It's another thing to say, given some beyond standard model theory, are there boson stars? How often are they paired up in binaries? How often do those binaries merge within the lifetime of our universe? Okay, so I think there's a lot of interesting work that can be done connecting these sorts of direct searches to then actually constrain beyond standard model parameters, but that's material for the future. I was meant to say that on the next slide. Oh, well. All right, let me just check my time. Okay, I'm running out of time, so I'm actually going to skip the next subject, which I'm happy to talk about afterward, and which is actually near and dear to my heart, because it's all about black hole perturbation theory and black hole ringdown. We can also use the final ringdown I mentioned before as a probe of new physics. And this is another very exciting branch of gravitational wave theory and observation, which has become very active in recent years. But in the interest of time, I'm going to instead move on to my final slides. These were the intimidation slides to convince you that I can still do calculations even after all these years. And I'll finish by just giving you a taste of what's ahead so that we still have time for a few questions. So looking ahead, as a summary of the topics I was going to talk about in this talk, I presented to you in detail the idea that we can actually do direct gravitational wave searches for the unexpected by looking for exotic binaries of, say, boson stars or gravitational atoms. What I didn't get a chance to talk to you about is how future precision predictions of how the ringdown of black holes will differ in theories beyond GR will allow us to do precision spectroscopic tests of relativity in the near future. Taking another step back to the first part of the talk, what's going on in the world of gravitational waves? Well, O3 yielded multiple new discoveries, including these puzzles, some of these oddball systems that we really need to see more of before we can begin to tease out population statements. We're actually in the middle of the next observing run. The first half, O4A, is completed. We're currently in a commissioning phase. We'll start back up in April. And during that first half of O4, we announced 81 significant candidates, okay? We haven't published any information about them besides what we distribute to astronomers in near real time so that they can search for counterparts. But that involves, say, the sky localizations and the significance of these events, as well as our best guess as to what they might contain in a very gross sense. So that means that we have potentially 2 neutron star black hole candidates that we've announced thus far publicly. But look at that. We had 90 detections over 3 campaigns, and in the first half of the 4th one, we're up to almost the same amount again, a demonstration again about how fast our data set is growing. In the coming years, we're going to keep improving the detectors until they reach and exceed their design sensitivity, which means we'll be detecting thousands of binary systems per observing event. And on top of that, additional detectors are joining the network. KAGRA has just joined and will continue to upgrade until it's a similar sensitivity as LIGO. And there are plans to build another LIGO detector in India, LIGO Ahunda, which will help us better flesh out the network and better localize gravitational wave events. But if we look even further forward, as I mentioned before, there are really ambitious proposals for new detectors, like the Cosmic Explorer detector in the US and the Einstein Telescope detector in Europe. These basically take very similar concepts to what our current detectors are and make them much larger to increase their sensitivity. The Cosmic Explorer concept is particularly simple in a sense. Just take LIGO and make it 10 times bigger. That will multiply our sensitivity by 10. That will improve our reach by a factor of 10. Of course, to do that, you have to make a 40-kilometer tunnel, which means digging through the Earth to keep it straight. So this is a big project, but one which we hope to find funding for and then build in the coming decades. Why should we build these really ambitious experiments? Well, as I mentioned before, we'll drop our sensitivity by a factor of 10. This plot shows us the reach of these experiments in terms of the mass of the system we find and the redshift that we search out for. So if we're talking about binary black hole systems, we will detect these systems out to a redshift of 100, well before any stars formed in the universe. What this means is we will see every single binary black hole in the entire universe, always. Okay, we will not miss any of them. If we're talking about neutron star systems with masses between 2 and 3 solar masses, we'll actually have a sensitivity out to a redshift of about 6, again, giving us the potential to detect every single binary neutron star merger in the universe. This is the promise of these detectors. They really open up a cosmological window for us to understand better the history of the universe. And of course, no talk would be complete without mentioning the space-based detector LISA, which was recently adopted by the European Space Agency, so it will fly in, I think, 2035 or so. This is a trio of satellites doing laser interferometry in space. They're much larger. They're off the ground, which means we can go to low frequencies and detect entirely new classes of system, like supermassive black holes emerging at the centers of distant galaxies. But with that, I'll thank you very much and take any other questions.
Thank you, Aaron. That was a very nice talk. Are there questions from the audience there?
Yeah, I was excited to see the potential within the Hubble constant.
Mhm.
Can you talk a little bit about what your current limitations are?
Yeah, that's a great.
Limited fully, or what's the?
Absolutely. So let me see if I have a backup slide that's more valuable to look at. Probably not. Okay, I'll just go to where we were looking at this. So the question was to say more about the Hubble constant measurement and what is limiting us at the moment. So there are a lot of limitations. We're basically statistically limited at the moment. The intrinsic systematic effects, if we're not careful, tend to arise at around the few percent measurement level. And those come from a variety of sources depending on the method we're using to make the measurement. So for example, if we are using gamma ray bursts as our tracer of the galaxies, we identify a gamma ray burst at the same time as the neutron star event to localize it. Our understanding of the emission pattern of those gamma ray bursts and how wide they are can create systematic sort of selection effects at the level of a few percent, if those are not understood. So we're well away from that for now, but with several more good multi-messenger events, we can sort of beat this down to about the few percent level. And one of my colleagues at UT Austin, Sin-Yu Chen, sort of has been driving an effort to really account for all of those systematic intrinsic errors, marginalize them out, and make sure that these measurements can go to the percent level or below.
Yes, I wanted to ask you about the boson stars. Is there a name for the theory that accounts for it?
Yeah, it is actually, let me see if I have a slide on this. It's actually just a simple scalar field model with a mass of the scalar field. Okay, when you couple that to gravity, you can have stable distributions, essentially a Bose-Einstein condensate, where the stabilizing factor is its own self-gravity. Now, how could such things form? Not entirely clear, although these stable solutions do exist, so you could imagine they might spontaneously condense, or they might condense in regions of high scalar field. This is just one example of such a model.
I was asked to review a couple of papers that had some statements about boson stars, but I've forgotten the name of the theory.
Yeah, and this is not my area of expertise at all. But the point, going back to sort of the effective field theory perspective on this problem, is that we can just use these as motivating ideas. But the real point is that if we don't know what these things are for sure, we just know that they're compact. We know for sure from an effective field theory perspective that we can model them during the in-spiral as point particles with some Wilson coefficients in the language of effective field theory, but with some particular properties. And we know exactly how those properties imprint on the waveform, and therefore we just promote those to free parameters and try to let those be a flexible parameter. Thank you.
Any other questions? Well, there were a lot of questions.
One more quick
Oh, sorry.
one.
Go ahead. Yeah, please.
So yeah, I mean, it's really exciting to see all of this continued development about ways you can use the data. You don't, this is an LHC person asking, you don't have trigger challenges. You're not doing anything to your data that means you can't go back to everything you've taken and look at it.
No.
Build sensitivity, so maybe you don't even care about the old data, but
Yeah.
it's got everything.
No, it's a great question. Compared to modern particle physics experiments, our data throughput could be kind of embarrassing, right? The signal is a single time series per detector, sampled at 16 kilohertz. So we're talking about tiny amounts of data. Now, on top of that, there are a huge number of sensors in the detectors which monitor the various detector elements all the time. There's about 1 million of these channels. So at the very worst, our data set is 1 million time series at 16 kilohertz. It is nothing. There's no problem storing it to disk. We have it on disk. We release at least the gravitational wave data fully publicly. Everyone can use and search it. That's why the Princeton IIS group was able to develop their own search and detect new binary black holes. Okay, so it's out there and available for everyone to use at the Gravitational Wave Open Science Center. But yes, we have everything to disk and we can go back for it. On the flip side, there are diminishing returns here, right? The same amount of data from the first observing run has 3 clear detections. The same amount of data in the 4th observing run would have, say, 100. So it becomes less and less useful to go back and scan the whole data set, but one can do that.
Okay, if there's no further questions, that's all. Thank you.
Thank you very much. Thank you, everyone.